Okay. So, hi everybody. We are reaching the end of the season of our seminar here at the Institute. So this week we have the last two seminars with two visiting researchers. So the first one is Dr. Georgios Loukes-Gerakopoulos, who is visiting CFIS and working with him this week. So briefly about Georgios, so he got his PhD in astrophysics from the physics department of the University of Athens in 2010. And then he moved to the Academy of Athens as a postdoc for a year. And then to Germany, to the Jena University from 2011 to 2014. Then he's spent 2 years as a postdoc at Charles University in Prague. And then finally, he joined as a researcher the Astronomical Institute of the Academy of Sciences of the Czech Republic in Prague in 2017. His main current scientific interests are the field of extreme mass ratio inspirals and gravitational waves. That is also the topic of today's talk, right?
Okay, thank you very much. And thank you for having the time this summer to come here and listen to me. And I will start with advertisement. So we are at the beginning of summer. At the end of summer, we have a conference in Corfu, which is about general relativity. It's the conference of the Hellenic Society for Relativity, Gravity, and Cosmology. And it will be held from the 1st to the 4th of September. Okay. And we have several important plenary speakers. I don't know if you can see. Until then, it's Leo Barak, Sebastiano Bernucci. Can you see at the back? Or okay. So the registration ends at the end of July. You have still time to register and contribute a talk or whatever you like. So having done this advertisement, and not. Yeah, see. Okay. Maybe I clicked. Great, thanks. So I'll move to my talk. It's mainly introductory talk. I don't know. I know that only there is a group from John Antoniadis who's doing the pulsar array. So it's lower at the frequency that I'm interested. I'll start from some basic things, and at the end, I will push you to my topic. And I would like to tell also a story. So I will go back to 1600s, when Tycho Brahe got a big fellowship from Rudolf II, the Holy Roman Emperor. And he was able to establish observatory in Prague. And since he had the data, he needed a theorist, so he needed a postdoc. So he was looking around, and he found Johannes Kepler. Johannes Kepler, however, was a monk, and since then they didn't have proper internet, so communication were by letters or whatever they used. When Johannes came, he was a monk, and Tycho Brahe was bigger than life. He was partying, it was luxurious life. And probably they didn't like each other too much, and Tycho Brahe decided that he won't give him for a year the data. So you're a postdoc with a data, you're frustrated, you cannot publish. In the year, however, Tycho Brahe unfortunately died. So Johannes got data, and he was able to publish 2 papers, the first Kepler law and the second Kepler law. And I think the first Kepler law is more important because as a monk, he believed in God, and God created perfect spheres. But he looked at the data and said, this doesn't fit. And he was able to push his perfect mathematical ideas about what God thinks to real things, and to simplify his model to ellipses. So this is the first Kepler law. We move on ellipses around the sun. So in that sense, this is also the story here. We have perfect models for modeling extreme mass ratio spirals, or we have not yet. I will tell the story also there. but we are pushing to that, and then we have to butcher all these things to make them usable for the real gravitational wave detection. So this is what is going on with the observatories. This is operating. This is John Aldoniadis realm, Santa Are, nanohertz. This is also operating. These are the terrestrial gravitational wave observatories. And some people say that since this is around what the ear of a human can hear, that if you are close to the black hole, since your ear will be stretched and pulled in different direction, you should be able probably to hear the black hole, but I will not claim that. Then, in this case, at this moment, we have, I would say, 4 candidates per week. But in the future, the Einstein telescope will come, and probably we will have every minute or few seconds detection. But apart from pulse array, so what you see here, sorry, it's frequencies. And here is the characteristic strain. The strain, if you're not familiar with the term, is, I will probably say how we take them. If the gravitational wave passes, my distance between us changes. So this is some kind of delta L, the change, divided by the distance between us. So this is plus or minus how you should imagine the strain. So as you see here, symmetric binaries, so binaries with equal masses. As we progress, we go to more asymmetric binaries where you have supermassive black holes playing a role. So this is the merger thing. So you will have also galactic binaries with symmetric masses here, but they will passing through to go and merge around the hertz to kilohertz bandwidth. So it's like electromagnetic spectrum. You have different frequencies, different phenomena, and we focus in the millihertz regime, where unfortunately, with instead of having discrete events, we have overlapping events, because you will have supermassive black hole merging, you will have extreme mass ratio, which I will describe like stellar black holes or stellar compact object in general, expanding to supermassive black holes, and you will have galactic binaries that are not at the merger stage, but they are coalescing, so they are coming together gradually by losing energy angular momentum. And all of this we will detect at the same time, all the sources. And this is a big difficulty, because as I will show you, in order to detect extreme mass ratio, we need some accuracy. And now you will have to go, and according to our data scientists and data working group, data analysis working group, they are saying we have to create a cocktail of all these waveforms, they call it global fit, in order to be able to discern all these things. Unfortunately, if you can imagine, for extreme mass ratio, you have a stellar black hole, which is smaller than a supermassive black hole. So the signal that it produces is much more smaller than a supermassive black hole one. So if you have at the same distance 2 supermassive black holes merging and another extreme mass ratio at the same time, probably the extreme mass ratio will be at the bottom of your sensitivity curve. So it will be very difficult. So this is the first challenge that we have to deal with. We will be deep buried in the signal. So after describing this, let's talk about the instrument we're going to use for this detection. Is LISA, the laser interference space antenna. It will be launched according to the current in 2035. This is the current program, but already people are speaking that probably will push it further away. So 2037. These are fortunate for people doing X-rays, because if LISA is pushed, New Athena is pushed also further away. So you will not have your new Athena, which will be X-ray observatory, probably around mid-40s, something like that. So the interesting thing is that you have 3 satellites. We have in the center of them 2 gold tubes, which are moving on geodesic orbit. And the spacecraft is being hit by solar winds, whatever winds, so it's being pushed, and all the mission is done in such way so the spacecraft has to follow these 2 tubes so it doesn't drift away. And you have to keep around 1 degree in this triangle, which is not very small. It's 2.5 million kilometers each arm, which will be quite challenging, but we hope that everything will work fine. Also, I will speak later on about working at the LISA consortium. I don't know if somebody has joined or interested in joining. There are 2 ways to join. Is as a consortium member, or which you don't have any, let's say, obligation to the consortium, and you can just watch what's going on, or as a core member, and then you have to have a pledge what you will do for the next year. You're reporting each year. So in Greece, we have created the LISA GR group, whose leader is Nikolaos Karnesis. And if you're interested, you can contact him, and he can give you some directions, or you can write to me, and I can give you some information about this. So how you can join the LISA mission. So this is plus minus the instrument. And now what are extreme mass ratio? I already mentioned this. We have stellar compact objects, black holes, neutron stars, orbiting around a supermassive black hole. And as they are losing energy angular momentum, they are gradually going towards the central supermassive black hole. And from that, we have this is the strain and the time. We create a waveform, and this waveform should be the pattern. I don't know if you're familiar with match filtering. It's basically like doing Fourier analysis. You try to match different frequencies until you find one, and then you have a peak. Here you have different templates, waveform templates, and then you try to fit them to the signal, and if it fits, then the Bayesian statistics says, okay, this is the best one, and you can find the proper parameters. Okay? So the whole thing is do the dynamics, find the waveforms in order to prepare the mission. And it's even more complicated because you have to put it in the global fit, so that it will be with other waveforms from other systems as well. So this is the setup, the modeling that we want to do. And why we are interested in this is basically fundamental physics, because you can imagine it like the energy angular momentum is being lost slowly. So it's scanning all the space-time gradually. So we have very detailed information about the space-time of a black hole. And you can say, oh, this is square, or we were wrong for a long time, and this is something, I don't know, dark star, Grava star, whatever you like, some very exotic object. Or so this is a way to test the kernels of black holes. And if you can also find something funny about the gravitational waves. So if you're losing too fast energy angular momentum and it's not fitting the GR prediction, then you have to be in alert. It means that you have to alter GR itself. So this is also included in this investigation of these systems. And there are some we don't have, from astrophysical point of view, we don't know how many merger we expect. The current estimation is from 0 events in the 3 years that we expect LISA to fly, or 1,000. So basically, we have no idea what's going on. So this will tell us something about the population of black holes, stellar black holes around supermassive black holes. And then there is some theoretical modeling okay, we use perturbation theory, and it can be used from planets to whatever you like, quantum mechanics, basic ideas. So, okay, so let's go to modeling. This is more general than extreme mass ratio. The extreme mass ratio lives in this realm, but I think it's, since this is introductory talk, I should talk about the whole thing. So the most precise, let's say, models or models of binaries and their gravitational waves coming from numerical relativity, where we have sacrifices, what we have to do, butcher a little bit our theories. You have GR, which is covariant, doesn't depend on coordinates, and then you do 3+1 splitting in order to be able to evolve the whole system numerically. This means that you're sacrificing already something, because you now with 3+1 splitting, which means that you have hypersurface of space, and you have some preferred time evolution, you sacrifices the dependence on the coordinates. So this is the most precise. Then you have post-Newtonian theory, and this is probably you have heard about it. You take the velocity with respect to the speed of light, and you expand basically the, let's say, the Einstein equation, which is not really until the first order you can do it, but later on it's more complicated. You expand the whole thing, and you have some models. You see it, you have to be far away, so the speeds are not relativistic. And then you have the perturbation theory, which I will talk about later. By basically what you do some small perturbation, and then you see what the equation tell you. You can even, for example, if you want quasi-normal modes, you ring the black hole and it will start oscillating, and you will get the characteristic frequencies of a ringing black hole. Or you can do another, the self-force evolution, which I will talk about, and this is the most, let's say, precise thing that we have. If you use gravitational self-force, you're doing everything fine, but it's very slow. And we have to do the simulations, all these things should be under a millisecond. So what you do, you need phenomenological models. So what you introduce is models like the effective one-body approximation, which is basically a reshuffling of the post-Newtonian terms, and it's basically a mapping of the binary system in a body, a single body moving on an effective gravitational metric. So what you do, you reconstruct a phenomenological metric where you have 3 parameters and you match them in this limit with numerical relativity. And this is this question mark. This is very old graph actually, but I like this question mark because this is that right now my PhD student is dealing with that, is trying to take EOP and fit it to the extreme mass ratio spiral. So to have an effective one-body model that covers all the mass ratio, all the distances. So a simple modeling, you take the secondary not to be spinning. So this is unnatural, but this is the first approximation. You take the background of a black hole to be described well enough by the Kerr spacetime. You think there is nothing, there is no halo environment, accretion matter, nothing. And the loss of energy angular momentum is adiabatic. So you, as I said, you're losing slowly energy angular momentum. Then basically what you achieved, you are shifting gradually from a geodesic to a geodesic. And this is, I don't know if you have heard about integrability. You have 4 degrees of freedom with 4 integrals of motion, because you have also the Carter constant. So your system is integrable. So the background which you're removing is actually a quasi-integrable system. And since you have a fast movement, which is the secondary moving around the primary very fast, and the adiabatic motion is slow, you can split the whole thing in a 2-time scale approximation. So we have introduced now some simplification. So I said that if you want to do it very carefully and be precise, we should use a gravitational self force, which is basically you take the G mu, and you take, this is your care, and this is the mass ratio, and you do the perturbation. So this is the first order self force, this is second order self force. And by doing that, you're able to model very accurately your extreme mass ratio spiral, but this is extremely slow. So what we do, we already have to somehow cheat to do something more, let's say, simplified. We use the Tarkovsky equation, which I won't analyze what is it, but it's a second order partial differential equation. Now you have the stress energy tensor of the source, which is a secondary body. And this can be monopole, this means just the mass, or you include the spin, or you include higher moments of the quadruple body, which is essentially important if you go to less compact objects like whiteboards, and you solve this equation. And this is equivalent with previous, when you average the dissipative force at the first order approximation. So this is also, if you don't use the spin weight and you use, for example, 0 here, you can have a scalar field instead. Or if you use -1, you can see the electromagnetic perturbation of the Kerr space-time. Or if you are interested in fermions, you can put -1/2. Basically, or this could be also plus. It's symmetrical around this sign, so it's minus or +2 for gravitational waves, minus or +1 for electromagnetic, etc. So we use this in our group, and what we contribute in my group is, and what we contribute mainly is to this term. We included the dipole term, which is the spin, and now we are pushing for the quadrupole. And we solve this equation. And this is much faster than solving the self force. So now the most important about the strain, about the waveforms, are their phases. You don't want to lose too much. And we'll split the phase in 3 domains: the adiabatic, which is basically the Tarkovsky equation, the first order dissipative average part of the self force. Then you have something like resonances, which is, if you know from pendulum, this is the mass ratio, and this is the width of the separatrix, basically. And then you have post-adiabatic terms, which are extra terms of the first order self force, like the conservative part, which we have ignored in the dissipative. So the conservative part, the easiest way to imagine is like you have a body that has its own gravity, so it's deforming the space-time below it. So you don't take into account the adiabatic, you put it in the post-adiabatic, so it's higher correction term. Or you have the spin term, which is also not included here, but it's included in the post-adiabatic. And we need, after several cycles, so the secondary is going around the primary black hole several times, and this several times is inversely proportional to the mass ratio. So if you have 10 to -5 mass ratio, then you have 10 to the 5 cycles, and there are too many cycles. So if you imagine what's going on now with the terrestrial, you have maximally 10 cycles for black holes, and few, let's say, up to 100 maximally, and this is exaggeration for neutron stars. And then you go here and you have something like 10 to the 5 cycles. So, and we need to be extremely accurate in order to get parameters of our system, so the masses of the black holes or the spins of the black holes. So this has to be, according to our estimation, about 1 degree. So after 100,000 cycles, you want to have an accuracy of 1 degree. And this is quite challenging. And we have not reached the point yet to have the whole thing, actually. But the mission is 10 years, so we hope until then to have this desired accuracy. And now I go to my research. So what I do is basically 3 things. I'm interested about what is the secondary spin introducing to your system. What is the environment doing to your system? So you have some accreting matter, it will change the dynamics. And the third thing is, because the extra thing include more degrees of freedom or destroy symmetries, you introduce no integrability into your system. Okay, so let's stay here. So what we have here, we have taken a black hole, we have put a ring around it, and then we show what's going on with the orbits. With us just Schwarzschild, a non-spinning black hole. Then we have the red one, and if we include the ring, then we slowly see a dephasing. So this is an example how the existence of some accreting material around the black hole can change your template, your gravitational wave template. Another thing that we actually avoided in this work is to deal with the resonances. And this is, if you do dynamical system, it's just a reminder what's going on there. This is imagine that you have tori in your phase space, you cut the tori and you're looking, it's like a donut, and you're looking what's inside, if you find chocolate or whatever you find. So here you have a resonance, and around it you have quasi-periodic orbits. A resonance means that your two of your characteristic frequencies are commensurate. Okay? If I break the integrability, then according to Poincare-Birkhoff theorem, the resonant torus will break and will create these complicated structures. And they are not of zero width like here, they have actually width. And while your body is spiraling through these resonances, it will leave a characteristic imprint that I will show in the next page. So this is important at the level, if you want to see what's to remind you here. This is something between adiabatic and post-adiabatic, and depends on what is going on with this epsilon perturbation parameter. So in our group, we are studying this. So we use, for example, if we include the secondary spin, how this will impact our waveforms, and the impact in this of the order 1, so of 1 degree, which is important for the waveform modeling. And then you can go and say, okay, it's not a care, it's whatever you like, the black hole, the central black hole, and then you can include a quadruple deformation and play with this and say, okay, I will have such effect. And this is what I told you about testing the kereness by playing with such models where you have a quadruple deformation, because from a black hole, classically you have just a pole and dipole. You don't have a quadrupole or higher multiple moments. You can tell in the affinity that the mass and the spin of the central object. What you will see, if you have this omega r, omega theta characteristic frequencies and the time progress, if you cross the resonance, you will see such. So here you have quasi-periodic orbits, you reach the resonance, and you have, again, the fall. If you want to see it in periodogram, then you will, this Kyriakos Estounis work, you will see a jump here. Otherwise, it will be just a continuous line. So really, this is something that can be detected. So the last part of the work is to include the spin of the secondary. And with Victor Scopy, who was my PhD student, we started from circular orbits with a spinning secondary, and we're able to push using two Telkovsky equation solvers. So you can solve it in the frequency domain, which means that you have characteristic frequencies that you know a priori. So you know that you have somehow approximated your system to be some semi-integrable, or time domain. If you solve it in the time domain, then you just have to have the orbit, you throw it to the Telkovsky equation solver, it tells you this is the fluxes that you get. And this was fortunate for us because we could push. We started from circular to eccentric orbits. We were able to compare two different codes, a frequency domain and a time domain, and see how they converge. And finally, it was the first work that was able not only to do the eccentric ones, because everyone until then was doing circular with a secondary spinning, to go over equatory, to have a first generic time we were able to recover fluxes, energy and angular momentum fluxes from a body with a secondary body with a spin that was moving in generic orbits of equatorial orbits. And this is where we end. So a summary. Basically, we expect from extreme mass ratio spirals to tell us something about our theories. Are the black holes described well by the Kerr spacetime? Is GR enough for modeling, let's say, our universe, our gravitational universe? And the challenges are that MRIs will be at the bottom of the sensitivity curve. So we might not be able to detect them, or that our, let's say, that we won't be able to reach the accuracy needed to do not the detection will be made if there is extreme mass ratio. It's probably we won't be able to estimate well the parameters. So the masses of the black holes in the binary, the secondary spin, etc. If you're interested in X-rays, I will do something. I will go back to this. So in my group, there is, for the last 4 years, people are looking what's going on when the spiral object is going through the accretion matter and perturbing it. And they are correlating it. There are several publications from Sukova and Vladimir Karas that are correlating this passing with quasi-periodic eruption in X-rays. So if you have heard about quasi-periodic eruptions, we claim in our group that they are probably from some kind of extreme mass ratio spirals, which are pushing the material out of the accretion disk, and then you have some, I don't know if you know about quasi-periodic eruption. They are soft X-rays, and you have several scales. You have a background, and then you have huge peaks of 3 magnitudes, probably out of this background. And in our group, we claim that this is probably from an object passing through the accreting matter. And to be sincere, I hope that this is the case, because I'm not very optimistic about doing it with ELISA, because as I said, if it's not near, signal is weak, and if it's not near to us, or I don't know, in Andromeda, in our galaxy, the center of our galaxy, we won't be able probably to detect extreme mass ratio spirals. But with this, probably if you have New Athena or other good X-ray detectors, or even some of the detection were done by multi, let's say, bandwidth explorations. We probably will see them because we can correlate, we will try to correlate the spiraling motion of the object with these outflows or shadowing of the black hole. So this is it. Thank you very much. If there are any questions.
Question here and online.
Thanks a lot for the presentation. I was wondering if you can go back to the simulations of the black hole and the ring.
Yeah.
Can you comment on two things here? So I would maybe assume that the matter that you include in the ring is significant, has like very large impact on the results. And the second thing, do you capture the evolution of this accretion disk, like how it's formed, or it's you set up the accretion disk?
We have an exact solution of a ring, Bach-Weil ring. This is so exact solution means that it, if you put it in the Einstein equation, you solve them. Okay, they are, and then we have truncated this just to have the quadrupole there. So the quadrupole of the ring. So we have a static thing, and we say, okay, it can be anything. It's static. It doesn't evolve. It doesn't have a dynamic. And we just wanted to do two things. We use canonical perturbation theory in order to simplify the system even further and to be able to have action angle variables to evolve our system. Because if you have the actions, so the angles are the fast, you can neglect them, you remain with the actions with R, which are your integrals of motion, energy, angular momentum, etc. So this was the game here. So we didn't take into account. So I don't show you the GRMHD simulation that we have done or are being done at my group because this is not. I'm not included directly in this group. Okay. But what they are doing at the moment, they have about the GRMHD simulation. You have the harm PI. You're familiar with. They have modified it a little bit, and then they are they are simulating the secondary black hole, like I would say, like a disk that's going through your accretion matter and pushing it up and down. So it's a very simplified model. Now we want to include the dissipation. So because you have energy and angular fluxes that are emitted, and the system is sparring inside, so it should change frequencies. And we want to include this in order to have more precise models and to be able to compare with them with quasi-periodic eruptions or quasi-periodic outflows, general quasi-periodic phenomena caused by perturbing the accreting matter.
I have one. So now you're talking about black holes spiraling, but at the beginning of your presentation, in this extreme mass ratio, you were talking about also compact stuff.
We don't have the compact. It's for Lisa. For Lisa, the enemies are either what we expect are black holes, so up to, let's say, maximally 100 solar mass black holes, or neutron stars, maybe white dwarfs. This is the extreme mass ratio spirals. If we go to what the LISA will detect, it will detect many things like supermassive black hole mergers, galactic. Basically, there are so many white dwarfs that they will create a stochastic noise background, which has to be dealt somehow. So basically, it's destroying our sensitivity curve because we cannot discern this There are so many, so we cannot discern. Even if they are very monochromatic, which means that they basically evolve with one characteristic frequency.
Okay, but so you are also interested on this neutron star or white dwarf, for example.
Yeah, because this is why we include the quadrupole term now, because if there is a white dwarf, there will be a deformation, it's less compact, so we expect it to have some kind of role in the waveform
So
modeling.
I may have a follow-up question on this. So do you also expect this star to lose mass because of some tidal force while spiraling?
It will lose probably black holes and neutron stars. No, they will just evaporate. There will be they will somehow just go and they will be gone inside the supermassive black hole. I will expect this also from the white dwarfs. But if you have main sequence star, yes, you will have some tidal destruction events, like you see in Sagittarius A, probably some stars that are just
And
falling
you're
apart.
not modeling this.
No, this is not. We focus on the compact object. This will be extremely more complicated to include main sequence stars.
But maybe also interesting, right? Because nowadays
We don't. I must be sincere. We can not even at this time fully model the black holes, because the second order still for us to be included. So they are sometimes still missing. So yeah.
Thank you for the talk. I have another question, more generally. What are the mass ratios that we're talking about when we talk about extreme mass ratio spirals?
It's
And to which point, does the range that you can kind of probe analytically change also with the kind of perturbation terms that you add?
so. This is the game that's being played right now. So people are trying to push. So numerical relativity is problematic that you can do something in this regime. But if you go to 10 to minus or 10 to the 3, the mass ratio is very here, 10 to the 3, the numerical thing is totally bananas. It's giving too much numerical noise. There are few, like Lusto group has done something, but these are extremes. Everyone is working in this regime. So what we are trying to push is from perturbation theory to match this realm and use the EOB as a guide as well. So people are looking, okay, EOB is, so the detection right now from the terrestrial observatories are using some kind of phenomenological model, and this is the EOB one, or phenom. They are different. But this is well calibrated to the current detections. So people are saying, okay, this is very difficult numerically and expensive, computationally expensive. Can we go from this to this? And they seem up to 1 to 10 to have a quite good agreement. But you won't use self-force. What you're hoping is to calibrate enough effective one body to cover all the distances, the distances and the mass ratios. So you need some kind of phenomenon, just like Frankenstein, you take different parts of theory and you can want to glue everything together. But this is the dirty work that you have to do in order to be fast enough and accurate enough to cover what you want to do.